what is biomedical signal processing? Yeah, so better not using this. Mm. In the previous session, we have this two sessions we have discussed about biomedical sensors and biomedical instrumentation. So in biomedical sensors, we have learned a little bit. We have got introduced to some devices used to tap the signal, yeah, from the body into the instrumentation. So we have reviewed some of these devices. Yeah, basically, those devices, biomedical sensor, convert physical or chemical signals or biological signal as well, biochemical signals into mostly electrical signals. And so if we have uh, here the subjects, in this case, when we speak about biomedical signal, biomedical instrumentation, we are always speaking about a human subject. A human subject. So first is this is the sensor will convert this into a mostly electrical signal, and as you have also seen from the video that I give to you, that the link that I have given in the group, yeah, by an Indian lecturer. So from here, mostly then there will be signal processing before the signal can be displayed. So here is uh, signal display. Signal display here is further divided into, among others, it could be displayed, yeah, as a monitor, for example, graphic display, could also be recorded. Previously, it was recorded usually in paper as charts, but nowadays with computers, you record the numerical data so that then you can easily plot it as a graph in any computers, yeah, recorded. But also then could be transmitted, yeah, especially with uh, internet, with telecommunications, with the advance in telecommunication technology, internet technology now, the signal can be easily transmitted to anywhere around the world. So the physician or the doctors, the specialists, do not need to be in the place of the patient. Although it is not yet widely used yet, this technology, but it is already possible. And later with the advent of 5G technology in the future, in the near future, not only that the physician, not only that the physician or the doctors or the specialists can get the data and read the data in after it is being done, but the physician or the doctors can also read the data in real time and also possibly do the therapy also in real time. That will be something in the future that also this will involve, for example, in future surgery. Yeah, this is already in therapeutic case. Yeah, well, this mostly is still in diagnostic part. Even now, the diagnostic part have not been done completely online or in real time. Mostly still in most of the clinics, even hospitals, they do it still offline. Yeah, but already data are being recorded. Previously, even in 20 years ago, mostly are still in papers, in chart paper, and the doctors have to, or the patient or the nurse have to bring this printed charts into the physician, into the specialist to get uh, their information being interpreted. And now, even with the advent of AI, artificial intelligence, yeah, some of this can also be recognition, yeah, signal recognition and interpretation. Interpretation. So, especially using AI. In my time, we already learned about artificial intelligence, but we haven't really applied it in actual healthcare. We just learn it for the sake of knowledge or for the sake of science. But today it is almost there. Yeah, the technology are there. So now people are developing this technology to be able to interpret the information, the signal automatically. So, for example, like if you know what Aulia is doing for his research, he is developing artificial intelligence algorithm, machine learning algorithm that can classify ECG signal autonomously, actually without the help of cardiologists, and then interpret it whether the person is healthy or not healthy. If not healthy, what kind of diseases he or she has. Is it arrhythmia, uh, uh, dysrhythmia, tachy, uh, tachycardia, for example, and many other heart-related diseases. So this can be now even be replaced by an automatic system, even though there is still some resistance from the doctors. Yeah? The cardiologists, they are not yet really want that their role is being replaced by a system, by a machine system, by computer. But like it or not, actually there is a need for that, because if we see our condition in developing countries, in Indonesia, we have remote regions. Yeah, our geography is we are archipelagic country with islands spread, yeah, in thousands of kilometers away. So, and most of the specialists, most of the good doctors live or resides in big cities, yeah, in Jakarta, in Surabaya, in Medan, like that. Well, in remote regions, even in West Java, for example, in the remote region in Tasikmalaya, Sukabumi, those in the villages, you cannot. It's very difficult for you to find good specialists. So how can we make a more distributed or evenly distributed healthcare service? One of that is by exploiting telecommunication technology and information technology, yeah, using AI, artificial intelligence. So there is more and more movement towards not only to display the graph, the data from instrumentation, not only to record the data, not only to transmit the data for telemedicine, but also to automatically recognize the data, to interpret the data, and give already ready information for either the physician or the patient himself. Yeah, and in the near future, this even goes towards therapeutic. So as I mentioned, we are moving towards this direction with the advent of 5G technology. Yeah. In 5G technology, the speed of the telecommunication get will be getting more enhanced, such that there is no latency anymore. Latency here meant the delay in telecommunication. Currently, if even for example, if you do telecommunication, yeah, the teleconference using Zoom or using video, sometimes you see some delay, yeah, between the voice and the image. In the future, this delay will be less and less, even less and less. So this is very, very important when you want to conduct, for example, telesurgery. So the surgeon might reside in Jakarta. The patient with the nurse may be somewhere in Papua, for example, and then the doctor see a real-time video imaging from the patient Papua, and then immediately operate some machine in Jakarta to operate, for example, the heart or the stomach of the patient somewhere there in Papua in real time. Without the 5G technology, this is not yet possible. With current telecommunication network which we have in Indonesia, 4G, it is not yet possible because there is still this latency between the person operating and the actual actuation by the actuator at the place where it needs. So, but for example, in China, they have already used this 5G technology, even though not yet in the healthcare sector. They use it in the industrial sector to operate, for example, big machinery, tractors, forklift, yeah, especially during the pandemic. And the operators just conduct the operation in some special room in near their house, and then the machine is on the field. So this is made possible using the 5G technology. Okay, so let's have a break for a while. Yeah. Sorry for the delay today because I have some meeting. Okay, so we go back. Yeah, to this. Now, what usually when we speak about signal here, yeah, so signal here is what the video that you have just uh, seen, yeah, yeah, what you have just seen in the YouTube, yeah, that will. There are many types of signal. Of course, one is one valued signal. This is like body temperature, something like that, yeah. But there is also time dependent signal. And many of our biomedical signal are time dependent signal. Yeah. So in this case that they are a function of time. Let's say for example ECG, yeah, electrocardiography. This is the signal from our heart. Yeah, usually then it looks like this. P, this is the P, and then Q, R, S, T. So this is the P, Q, then the R peak, S, then there are small peak T here. Then again another P, Q, R, S, T, etc. Okay. This is usually is voltage because we are measuring in voltage because the ECG measure the potential between two or three or more of potential difference, yeah, of places in the body, mostly near in the vicinity of the heart. So this is a time domain signal. So in time domain signal, mostly we express a signal in three parameters. Yeah, in three parameters. What are they? They are voltage or the amplitude. Yeah, the amplitude. Then we have the frequency of the signal. Then we have the uh, phase of the signal. So this is if you know from mathematics, yeah. Usually we express time domain signal in terms of sinusoidal signal. So if we have only one single sinusoid, yeah, for example, like this, yeah, this is a sinusoidal signal as a function of time. Let's say this is a function of voltage. Okay, then the amplitude is the peak value, the value of the peak. Yeah, here, this is the amplitude. Sometimes we want also to see peak to peak value. So amplitude, peak to peak. So here, so if only just amplitude, usually is from the zero level to this one. But if it were peak to peak, usually from the positive peak until the negative peak. This is amplitude peak to peak, PP. The frequency is the second, yeah, the second parameter is the frequency. It indicates or it shows how many times that signal uh, repeat itself every second. So, for example, if you have a sinusoid like this, right? It repeats itself from, for example, this is repeating itself, or this peak is repeating itself at here. So basically, the period is when it form a single wave, a single full wave, for a single full wave. This is what we call as period, right? How many seconds? So then the frequency can be defined as the inverse of the period, 1 over t. So for example, if we have a sinusoidal signal whose period is 1 millisecond, it means that the signal repeats itself every 1 millisecond. So the frequency will be how many? Anyone? No one? Is everyone still alive here or sleeping? Hello.
Itu itu 1 millisecond ya, sir?
Yes, if the period is 1
Periodnya.
millisecond, yes, the frequency will be
1000
yes. So the frequency will be 1/t.
hertz.
1/1 million. 1 millisecond is 10 to the power of -3, right? So this be 1000 cycle per second, or the unit is hertz. Okay. So this is the second parameter. The third parameter is what we call as phase. Phase is how much time it is lagging or leading. So for example, if we have another wave that when the t equal to 0 is already in its peak here, so we know that it is leading by 45, sorry, by 90 degree, right? Or by, usually we express the phase in radian by pi over 2 radian. So pi over 2 radian equals to 45 degree. Yeah, because at, sorry, 90 degree, yeah, 90 degree, 90 degree. So because at t equals 0, in normal sinusoidal, it is supposed to be the sine 0 is 0, right? But this red wave, by time t equals 0, it's already sine 90 degree. Sine 90 degree is 1. So we can express then the black wavelength as, for example, as this one, y equal, let's say the peak is a, sine, the frequency is 1000 hertz, and so usually we express the sin omega t, where omega is the radian frequency. Radian frequency or cyclic frequency is defined as 2 times pi times the frequency. So in radian frequency, it's not anymore cycle per second, but instead it is radian, how many radian per second. So let's say if it is 1 hertz, 1 cycle per second, it means every second it is 2 pi, right? Every second it is 2 pi radian. So the omega will be 2 pi times 1, 2 pi per second. 2 times pi, 6.28 radian per second. So in the case of 1000 hertz frequency, then the black wave here is y equals to a sine 2 pi 2000 pi t, sorry, t times t. Okay. While the red one, the red wave here will be y equals to y dash, let's say y dash. Okay, the amplitude is the same. Yeah, equal sine 2000 pi t, and then plus pi over 2. So this is the phase. And so because at t equals 0, it already has a phase of pi over 2 or 90 degree. That's why the value of the red one is 1. Yeah, not 0 anymore. Okay, this is safe. That's now clear. Okay, so sometimes, or not sometimes, many times the signal, like ECG, what we have seen, what I have just drawn, the signal can have multiple frequency, multiple frequency. So the signal can consist of not only a single sinusoid, but instead can consist of multiple sinusoid like this. And then you have, with having a frequency of f1, let's say, then we have uh, another signal consisting of frequency equals to 2f1. So this, it means it will have the amplitude is the same. Let's say the phase is 0, so it's having the same phase at t equals 0. So if we draw it, it will look like this. So something like this. See here. So it is twice quicker, yeah, or 2 cycles more than the first signal. Then the overall signal will look as will be y equals to a sine 2 pi f1. This is f2, yeah, plus a sin 2 pi f2. Okay, so this will look like something like this later. Yeah, something like that. So it because it has uh, two frequency. Yeah. So and we can add more. For example, not only two frequency, but even more than two frequency. So when the frequency is a multiplication of a base frequency, the next frequency. So for example, we can have F3 equals to 3F1. We may also have F4 equals to 4F1. Yeah. So when we draw the signal, then we will, so we have this addition, summation of all this frequency, and this is what we call as harmonics of the base frequency. So the base, this is called as the base frequency, and the other frequency are called as the harmonics of the base frequency. So the two will be the second harmonics, we call it, three will be third harmonics, the fourth F1 will be called as the fourth harmonics. Okay. Now, when we conduct signal processing, sometimes, like let's say the ECG, yeah, the previous ECG signal example, P and then Q R S T, P Q R S T. Okay, sorry, nah, like this, for example, right? This will contain much more frequency than just one single frequency. Right? First, it is not sinusoidal, but we know it is periodic. Then we need to do what we call as frequency analysis. So from this is the when from time domain time domain, this is T, time domain signal, voltage as a function of frequency. We would like to change it into frequency domain uh, signal. So we want to know the frequency component of the of this signal. What is it made of? Yeah, is it made just from a single frequency? If it is like this, if it is F1, F2, F2, which is 2 times F1, this is the harmonics. But a signal like ECG, which is more irregular, consists of more than just the harmonic, the base frequency and the harmonics, but contain also other signals. So this can, so usually in the case of ECG, the bandwidth is until 100 hertz. Yeah, about 100 hertz, the bandwidth, we call it as a bandwidth. The bandwidth is the signal having frequency, the range of the frequency of the signal that form a time domain signal. In the case of ECG, it will be about 100 hertz. In the case of EEG, electroencephalography, brain, the bandwidth could be up to 1000 hertz. Muscles, EMG can be around tens of hertz, several tens of, several tens of hertz. Okay, the tools to transform from time domain signal into frequency domain signal is usually called as Fourier transform. Okay, Fourier transform. If the signal is still simple like this, yeah, consists of uh, frequencies which are basically the harmonics of the base frequency, then we can use Fourier series to express it, yeah, because the signal is still periodic. But when the signal already contains a lot of non-periodic component, then we have to use Fourier transform. And when we do it in computer, the algorithm is usually called as fast Fourier transform, yeah. FFT. This is the algorithm used in computer usually to convert time domain signal into frequency domain signal. Okay, and why do we need to analyze a signal into the frequency domain? Sometimes not sometimes, yeah, many times the signal that we obtain from our instrumentation, yeah, from our our amplifier and then our sensor, and then we amplify it and then we filter. It's not smooth. Yeah, sometimes like this. This is the ACG signal, for example. is there is a ripple here. Yeah, there is a ripple, high frequency ripple. Yeah, overlapping with the original signal. So when we put this into frequency domain, we will see that, for example, this one will be from particle frequency, usually from the electricity line, 50 hertz. Okay, the other one is like this, the other frequency component. And then we can use filter to get rid of the signal which we don't want, or the noise. Yeah, the noise. The noise are signal which we don't want, basically. That can either from the instrument itself, can also come from the environment, can also come from the subject. When the subject move, okay, when the subject move, this ECG signal may be drifted. For example, it become like this, like this. Yeah. So instead of flat like this, it becomes like this. This is a low frequency noise due to the motion, for example, of the patient. Then this can also be eliminated using filtering. But to be able to do filtering, we have to first transform the time domain signal into frequency domain. So we know the noise. Which one is the signal, the original signal from the heart that we want to measure, and which one comes from the noise. Okay, let's set this and then clear. Okay, then another things which we need to know. Usually, the original signal comes from the sensor, and then the amplifier is in the form of analog signal, and this one is digital signal that is processed by the computer is or recorded is in the form of digital signal. What is the difference? So from analog to digital, we need ADC. So for example, if we have analog is when we have the signal continuous, for example, like this, continuous in both time as well as in value. Both is in time is not disrupted. In value also it continues from this zero value to, for example, a maximum tenfold, for example. But when it goes to analog digital converter, first it will be sampled. This is what we call a sampling period, sampling stage. So the sampling means that it will be cut off. Yeah, will be cut off at certain place. Yeah, like this. So we will have instead this signal. This is called as discretized signal. Discretization. Yeah, discretized signal. Time time discrete signal. Time discrete signal means that it is not continuous anymore. It means it only has value at certain sampling period. This is 0, this is t, this is will be 2t, 3t, and then n, etc. until nt. So t here is the sampling period. So for example, if we have a signal, let's say ECG, we can sample every 1 millisecond. Yeah, the 1 millisecond is the sampling period. It means the sampling frequency will be, this is the sampling period, 1 over Ts. Yeah, the inverse, so similar like the formula for period and frequency in the continuous signal. So if we have 1 millisecond sampling period, means the sampling frequency will be 1 over 1 millisecond. It will be 1000, not hertz again. Usually we call it as 1000 sampling per second. Yeah, we can call it hertz, but mostly in analog to digital conversion, we call it as one sampling per second or 1 kilo sampling per second. Okay, so but this is not yet finished. After discretization, what happened in an analog digital converter is that the signal will get quantified, quantization. What does it mean with quantization? It means that the signal, the value of the signal will be quantized like this. So for example, depending on how many bits you have. So for example, let's say you have 7, a value of 7, right? This in the bit, it becomes, because in computer, we only work with 1 and 0, 1 and 0, right? 7 is 2 to the power of uh, equals to what? 4 plus 2 plus 1, right? So this we come to the power of 2 plus to the power of 1 plus to the power of 0. Or if we express it in 8-bit value, this becomes 0, 0, 0, 0, and then 0, 1, 1, 1. Okay, so there are 8-bit values. So similarly, this one, the value here will be quantized. So if we have 8-bit, it means that a maximum 8-bit is 256, right? 2 to the power of 8 equals to 256. So we quantize this value into 256 level, 256 level. So if we have the full range is tenfold, for example, the full scale range is tenfold, each quantization level will be tenfold divided by 256. How many? So please calculate it. So we not only that the value in digital signal will be discretized like this, but it will also be quantized. So in it will be in block like this, something like this. Okay. So with analog digital conversion, we lost the signal in between the sampling. So the signal here will be lost. And secondly, we will also lose the signal between the quantization value. The signal in between will also lost because it is being rounded, either rounded down or rounded up. Okay, so in analog digital conversion, to summarize, there is discretization and quantization. And in order that we can reconstruct the original signal from the digital signal, yeah, usually then the sampling frequency here, the sampling frequency has to be at least twice the maximum frequency of the bandwidth of that signal. For example, for ECG, right, the bandwidth is 100 hertz. If we want to be able to reconstruct the original analog ECG using our computer, then our sampling frequency in our ADC have to be at least 200 hertz. The more, the better. 300 hertz, the better. 400 hertz, better. 1000 hertz, even better. Okay, this is what we call as the Nyquist sampling criteria. Nyquist sampling criteria. This is in terms of sampling. Then in terms of quantization, yeah, the more digit we have to quantize the value of the analog signal, the higher the resolution. The resolution is better. So for example, our full scale range is tenfold. If we have only 4 bits, yeah, so the resolution will be tenfold divided by 2 to the power of 4. So tenfold divided by 16. How many is this? About 6.0675 fold, right? So each level in that 4-bit only 0.0675 fold. So if you have a value of, let's say, 0.02 fold, it will be gone. It will be rounded as 0. So what if we want to then if we want to have less error due to this rounding, due to this quantization, then what we can do is increase the bit, the resolution of the ADC. So becomes, for example, 8-bit. If it becomes 8-bit, then the resolution will be tenfold divided by 2 to the power of 8. Tenfold divided by 256. I don't know. I don't have calculator ready with me. If you can calculate, yeah, this can. Yeah. So this is much. The value of this will be much smaller than this one. So it means you can quantize, you can approximate the value of the original analog signal better. So the filtering itself can be done at the analog level. We have what we call as low pass filter. So in low pass filter, so if this is the frequency domain, and this is the signal, the low pass filter will pass only the low frequency from this cutoff, what we call as cutoff frequency. The frequency, the signal having larger than this cutoff frequency will be filtered, will be stopped. In high pass filter, it is the other way around. In high pass filter, signal with frequency, for example, if we have signal like this, it will only pass Yeah, the signal at this frequency larger than the low cutoff frequency. We have also what we call as band pass filter. Band pass filter. What is band pass filter is if we have the filtering is like this. So we have two cutoff frequency, low cutoff frequency FC1 and high cutoff frequency. So signal below this FC1 will not be passed. Signal above FC2 will not be passed. We have also band notch filter. This is especially, or just notch filter, especially useful to cut frequency from particular frequency. For example, for due to the electrical line, usually 50 or 60 hertz. So it will pass the signal below that notch and above that notch. So only at the signal, only at that notch, the signal will not be passed. So this is all in frequency domain. Okay, with that, would be enough. Any questions so far from all you? No questions? Andy, Ezra, Anjali, Grace?
Not yet, sir.
Not yet. Okay, good. Then I will ask the question then, since you have no question.